So now we're going to apply the same strategy, but looking at a situation where you are dividing two numbers. So you're taking the log of a division. So we're going to go back and use these same properties. We're going to replace m and m, which is funny, with, laugh track, insert laugh track here, that's right, with these a to the b and a to the c. So instead, though, I'm dividing them. So log base a, the m was a to the b, and the n was a to the c. Now, just like in the last proof, we used an exponent law when we were multiplying. So here, we're going to use an exponent law when we divide. So what happens when you divide powers of the same base? We subtract what? We subtract the exponents, that's right. So it'll a to the b minus c. We subtract. Now again, we're in one of those properties from yesterday, okay, that says, what exponent do I put on a to get this power? Well, obviously the exponent is right there. What exponent do I put on a? Well, it's right there. So this log evaluates to b minus c. And if we look back in our notes, b is log m base a, and c is log n base a. So this is log m base a and minus log n base a. So really, I don't think this one should be much of a surprise. If the last rule or the law says if you're taking the log of a product, you can split them up and add. Here, if we're taking the log of a quotient, you can split them up and subtract. So if the other one was called the product law, what do you think this one's called? The other one was called the product law. This one's called the quotient law. That's right. So the quotient law it says if you're taking the log of a quotient, you can split it up into the log of the first one, subtract the log of the second one. Or vice versa. If you have the log of two situations where they have the same base, and you're subtracting those logs, as long as they have the same base, you can combine them and divide. So again, there's the property as a pure mathematical proof. Let's see it using numbers. So again, the first one is just applying the law, so just using it. So here's a log. It's base 10. I don't necessarily have to write the base 10, but that's no big deal. And it's 1 divided by 9. So I can split it up into log, keep the same base, of 1 minus the log of 9. That's applying the log. I can actually make this one a little bit easier because one of the properties from yesterday that says if I'm taking the log of 1, regardless of the base, what's the answer? 0, that's right. Because remember, this is asking what exponent do I put on 10 to get a 1? So 10 to the 0 equals 1. So this actually can even reduce to log 9, negative log 9, base 10. That's just we could go a little further simply because we had that 1. Sometimes if it was a 2 or something, we'd be done. Again, it gets interesting when we go the opposite direction. So for this one, again, you should notice that both of these logs have the same base. Their base is 6, and I'm subtracting them. On their own, they might be difficult logs to evaluate. So for example, what exponent do I put on 6 to get 648? I don't know. What exponent do I put on 6 to get a 3? Again, not too obvious. Like, what exponent do I put on a 6 to get a smaller number? That's a challenge. But if I use the laws of logarithms, maybe I can make this easier. So since they have the same base and they are being subtracted, I can combine them into a single log with the same base and divide their numbers. So 648 divided by 3. So that division actually ends up being 216. And now, can I do the logarithm? Well, sure, do a test on your calculator. 6 squared is only 36. 6 to the power 4 is too big, so it's 6 to the power of 3. But you'll see how each of the individual logs I couldn't have evaluated on their own. They weren't easy to do. But by combining them using the law of the quotient law, I ended up with a logarithm that was possible. It's not always going to work that way, but it does on that one.